Alright, hey guys, so today we are going to be doing another fluid flow analysis. I'm going to show you how to look at different uh, types of plates in a tunnel to show flow separation. So same thing in our Ansys workbench, we're going to use the fluid flow fluent analysis system. We're going to go into geometry. Once again, I'm going to use Design Modeler, but you are more than welcome to use Space Claim. I just find Design Modeler easier to use, so that's just me. Alright, so if you didn't watch my first video, we're just going to hit the Z-axis as we're doing everything 2D. We're going to look at our XY plane and go into the sketching mode. Um, so I'm going to test 4 cases, but I'll show an easy case, which is just making, well, you know what, let's do something. So if you want to test different angles of plates, it's actually pretty easy. You want to snap to your x-axis, and depending on what kind of angle you want, you can either do it this way, or, let's say you wanted to make it a little bit more aerodynamic. We're just going to keep it this way. Obviously, with aerodynamic, you would just start at the origin. I mean, so the flow looks like it would flow better, but um, we're just gonna make a line here. We're gonna use dimensions and angle. We're gonna select the x-axis in this line. Oh, sorry about that. All right, let's try that again. X-axis, this line. Oh, you know what? Hold on one second. I might need to give it a reference point. Snap these guys together. Okay, let's try that again. We'll make an angle. Select this and this. Alright, sorry about that. Alright, so I deleted those 2 lines, drew one from the origin, and then connected another line at the end of the first line. So now we are going to go and select angle, take it from the bottom, or the horizontal, or I'm going to mess up again. That's okay. Let's try this one more time. We only want the angle between these 2 lines. There we go. Okay. So now that we have the angle between these 2, we are going to check this out. And so the angle is 25, and some change. So we're going to head change it to 30 degrees. So you don't have to do too much with that. And then what I'm going to do is, actually, I'm going to select this line. I'm going to delete that. We don't need that anymore. And our geometry today is going to be I'm going to use a 3-point rectangle. I want a 5 by 50 centimeter plate. This doesn't really matter. I'm just going to click into that so that way I know it's on the line. And we're going to make our rectangle. Then we're going to go back into dimensions. And we're going to use general like we did in the first video. And we are just going to extend these out. And we're going to assign our own dimensions. Okay, so we're in meters. So we want this to be 50 centimeters long. So that's 0.5 meters. Then we want this to be a 5 centimeters, so this is 0.05. And obviously that looks really tiny, but that's okay. We could have changed it over to change the units on this. Not a huge deal. We are just going to zoom onto this model. because we don't care too terribly much about how everything looks right now. We just want to get a general idea of the shape. And then we're going to make another rectangle over this guy. To act as our boundary system for it. Okay, that's pretty much all you have to do. So if that was a little bit fast, you create a couple reference lines. That doesn't matter what the angle is. You use the angle tool to drag the angle out between the x-axis or your bottom line and your top line. Then you use the rectangle, the 3-point rectangle to follow the line that intersects with the x-axis, and then use the line itself to snap to, and then extend that out, and then you'll use the dimension tools to create your own dimensions, whether that's, right now we're using 5 centimeter thickness with a 50 centimeter length. So now that we have our sketch, we're going to go to concept and make a surface from the sketch. It's already selected. We're going to hit apply, and then we're going to hit generate, and it'll give us our geometry. Perfect. And that's it for here. We're going to close this out. Go to mesh. Now if you're like me and you are using the student version of Ansys, you have a limit to how many nodes are available in your mesh, which I believe is 550,000. It's not that difficult to hit if you are trying to if you're messing around with the mesh a little bit too much. But I'll show you how to find that and kind of what to look for. So once again, hit that Z-axis to center it up for us. And we're right click on mesh, insert a method, and we don't really care too much. We're just going to do automatic method. Select our geometry, make sure we apply, and then what we're going to do is insert a refinement on this, and we're going to hit apply. So one of the things we can do with this refinement is when we hit generate, refinement's going to try to smooth out most of the mesh that gets created. Refinement of 3 is usually pretty good. Anything more might give you some issues. So our element size right now, was 0.292. We're going to reduce that pretty much by 1/3. So just make it 0.1. We'll go ahead and update that mesh. And it's going to just make those squares a little bit smaller. So for automatic method, we have our refinement. I want to bump this to 3. This is just going to refine those little circles. I will update, or refine these little blocks that create our mesh. So now you can see it's a lot better. So the way to look at that and make sure you don't have too many nodes is we want to go into statistics. So right now we have 19,496, which we kind of want like 100,000. So one of the things we can do, you can either do it in here, change the element size. Let's make it 0.05. Let's try that again. We'll update it. It's not quite linear, so it's not going to mean it's going to be, 40,000. It's going to be a little bit, more fine. That's looking pretty good. You can kind of see some strange contouring in here, but that's not a big issue. So just to double check, we'll be fine with this. The more nodes you have, the harder some of the calculations will be for your computer. So if you have like a laptop that you're using this on, or a slower processor, um, it could take a while to do calculations. But you know, 75, 77,000 nodes, that's good. That'll for what we're doing. We don't really need too many. At least in a school sense. Obviously, if you're in industry, this might be useful. You'll have a more work-oriented computer that can handle much more nodes, and you'll be using, not the student license, or at least not in my case, using the student license. Um, so, like in the first video, we're gonna name some edges uh, so that way when we plug it into our solutions, we have some reference points to take some measurements from. So right click and then you go down to create name section, and we're only using velocity inlet. You can just put inlet. Um, I just like it. I like to name it so that it makes it a little bit easier when I'm looking at the results. And this is going to be a pressure outlet or regular, or just outlet. It's defaults to pressure outlet. We're going to select the top and bottom, and we're going to actually select that as symmetry. It usually creates a symmetry selection by default, but we're going to create ours just in case. And then inside here, this section that's actually not created, or not generated as an object, but more of a whole. This is going to be like if we were putting an objects inside of a wind tunnel, to see how the flow interacts with this object. You can do this more in depth by creating different parts and then placing it in. This is just a simple case to kind of show how it works. So this would be my top wall. This would be my front wall. And obviously you're free to name these whatever you want. I shouldn't have to tell you that, but whatever whatever floats your boat. Be the rear wall. And then just click on name selections, make sure that those are all there. This button up here I'm clicking is zoom till selection. That fits, kind of just looks at the object and fits whatever it can in. I'll double check. Got our velocity inlet, pressure outlet, our symmetry, which is the top and the bottom, the top wall of our object, the front wall, bottom wall, and rear wall. Awesome. Alright, so we're good with that. We'll close that up. Nope. Cancel that real quick. We got to make sure we update our mesh. Alright, so now that our mesh is done, we'll go back into setup. We want double precision. Don't worry about solver processes or GPUs unless you know what you're doing with that. Alright, so in the first video that I showed you, we changed some properties of air. Well, we're going to change the model real quick. So in this kind of flow, we're going to use K epsilon instead of K omega. We don't need to change any of these values, but what we do need to change is we want enhanced wall treatment. Alright, sorry. Yeah, we want the enhanced wall treatment and pressure gradient effects. This will be important later when we run our simulation or our calculations. Okay, so in the first video we used air as our fluid and we changed our density to 1 and our viscosity to 0.0001, we're actually going to keep these two variables the same, or these values the same. Um, Obviously, because we can't easily change some of the properties of air. Um, but what we can do is we can change the velocity at which the air comes in pretty easy. Um, so for this, we want a Reynolds number above 500,000 because we want a case where uh, we're going to experience, some turbulence. So let's swap over here real quick. So I'm going to show you, obviously, if you remember our formula was our Reynolds number equals rho velocity, and let's just use h for the horizontal length, um, over mu, which is the viscosity of our fluid. So density of a fluid, the velocity at which the fluid is traveling, the length of our plate, or horizontal length of our plate, I guess the effective length. And so we want above 500,000. So we want this to be above 500,000. So we already have our density, which is 1.225. We need a V, it's going to make it above that. And then our effective length is actually in meters, which is 0.5. I think this is kilograms meter cubed. It ends up being unitless, so not a big deal. And our bottom is like 5 point, what was that number? 1.7894. All right. And so the math works out that V to equal 500,000 is like 14.67 meters a second. So we're going to plug in 15 meters a second, which is going to give us something like 520,000 for our Reynolds number. Um, if you don't trust me, plug it in your calculator. But the math checks out. All right. So we got that set. We have our velocity set to 15 meters a second. Um, we don't need to change any other of our reference items, but we are going to go into initialization, make sure we initialize, go into our calculations, same deal. You can use 500. These are typically a little bit more complex. It should still converge around 80, but I'm going to put 1,000 in just in case. It looks like it goes pretty crazy, but it's gonna settle down real fast. Awesome. Okay, cool. So we'll double click on our contours. We can check our velocity contour. Let's just do that. And yeah, I mean that looks about right. looks about where the flow separation is going to start, or where we see our velocity start to slow down because of turbulence. Oh, sorry, we can fit this over here. I'm going to close this up. One thing I didn't show you guys in the last one was how to pull out some values based on values based off of the calculations that you just ran. So we can actually look at our uh, forces on our object by just taking, all these zones and hitting print. And it's actually going to put that into the console that we have here. So we can see all of our forces and yeah, the pressure, viscous, total forces, and coefficients, which will be useful. Um, so you can. This is kind of nice that you can print out your values for this. Um, but what we care about today is flow separation. So what we're actually going to do is we're good with this. We're going to close this up, and I like to use settings for current and future because if you're going to test multiple cases, you can save that. All right. So now let's refresh this. Update that. It's supposed to update it on its own. Not a big deal if it doesn't. And then we're going to go into results, and that's how we'll be able to look at our flow separation. All right, it should be done here pretty soon. All right, sorry about that. The solution took a little bit longer to calculate, and we're back now. Okay, so we're going to open up the results page, and we're going to jump in and do a couple things. All right, so how we did last time when we added our contours, we're going to do a velocity contour. Oh. We'll use 50. We want to use our symmetry that we created uh, as our location, and we'll just use velocity. Oh, sorry. Nope. All right, symmetry 1. All right. So that looks correct. We're good with that. We're going to add a pressure contour as well. And this will be just the same. And this kind of just shows, the pressure gradient as the flow travels over the plate, and you can kind of see where uh, that turbulence starts getting created, and then where it starts to kind of become normal again. Obviously, a much larger boundary section would show this a little bit better. All right, we can kind of overlay it and see where all that's happening. And then the next neat thing we're going to do is we're going to add some vectors. And we're going to do I'm going to call this flow separation. You don't need to call it this. This is just using it to show for us to look at our flow separation. We'll keep this as 1. The factor just increases or decreases the distance between. So the smaller this factor, the closer those arrows are going to be to each other. This is fine. I actually use 0.5 for my symbols, just so that they're smaller. Sorry, we gotta check. We gotta actually pick our location. All right, so this kind of looks similar to our, uh, our velocity. We can actually put our contour over there. So it looks, almost identical. Um, but this is going to show us where that velocity is actually going. So you can kind of see these are all actual little arrows. Let's pick this big spot. And you know what? Let me make this 3 for now so you can see the shape of the arrows. So you can see all these little arrows kind of going in different directions as it hits the plate, travels down and around, hits plate, travels up and around. But what we're interested is the flow separation where we start getting that flow that starts to go back. Where it starts to return. And we can kind of see that right here. So it starts, obviously it's starting to come up and in and, um, you know, up and in, but that's from where where the origin of that is going to be right. We can kind of see it right around here. So right here is where that flow starts to come back around. And we can kind of scooch in a little bit more. Yeah, so these arrows start to look like they, start turning back in and coming back towards the plate. So that's about where our flow separation is going to be. On the top side, on the bottom side, it's going to be a little bit different as well. You can kind of see it right around here. Start to come back in a really big spot right here. Same thing with this really big spot right here. Um, but yeah, so that way there's how you can show your flow separation. All right. So hope that was helpful for you guys. If you have multiple cases, you want to show a flat plate, you want to show a 90-degree plate, you can make airfoils, you can chamfer these edges, you can change some of the geometry to this and make it more aerodynamic and, get an idea of where that is. Obviously, a teardrop shape would be the most or the best way to kind of see this and see not necessarily flow separation, but how different shapes could mitigate that flow separation. But thanks for watching. All right, have a good day, guys.